In this video, we are going to talk about lightweight management of resource-constrained sensor devices in Internet of Things, a research paper done by Zhenguo Sheng, Hao Wang, Changchua Ying, Ziping Hu, Sushen Yang, and Victor C.M. Ling, which gives a co-op-based device management solution to allow easy access and management of IPv6 sensor devices. The concept of Internet of Things, also known as IoT, can be traced back to the pioneering work done by Kevin Ashton in 1999, and it is initially linked to the new idea of using RF identification in supply chain. Since recently, this term became popular and is well known as a new communication system where the Internet is connected to the physical world via ubiquitous wireless sensor networks, also known as WSNs. Generally, sensing devices are with common features of constrained energy resources, limited processing capabilities, vulnerable radio conditions, and no direct human interaction. By interconnecting sensor devices using low-cost wireless communication technologies, which is usually named as WSN, a new ecosystem with large number of smart applications has been formed. With the development of IoT technologies in the past few years, a number of major standardization alliances are gradually formed based on their interest in technology selections and commercial markets. Technically speaking, current IoT solutions can be categorized as non-IP-based solutions and IP-based solutions. Most of off-the-shelf solutions belong to the former, especially for some well-known standard alliances such as Zigbee and Wave2M for office and manufacturing automation, and wireless HART and Profibus for real-time industrial control systems. However, most of these non-IP solutions are isolated within their own vertical, which hinders the IoT development due to the incompatible nature across heterogeneous communication systems. Motivated by the fact that the Transmission Control Protocol and the Internet Protocol, also known as TCP/IP, is the de facto standard for computer communication in today's networked world. IP-based solutions could be the future of IoT networks. IP Smart Object Alliance, also known as IPSO, actively promotes IPv6 embedded devices for machine-to-machine learning applications. In order to tackle the technical challenges such as extensive protocol overheads against memory and computational limitations of sensor devices, Internet Engineering Task Force, also known as IETF, takes the lead to standardize communication protocols for resource-constrained devices and develop a number of IP, including IPv6 low-power wireless personal area network, known as 6LoWPAN, and Constrained Application Protocol, known as CoAP, and Routing Protocol for Low Power and Lossy Network. Although a wide range of intelligent and tiny sensing devices have been massively deployed in a variety of application environments, many challenges remain, which are mostly due to the complex deployment characteristics of such systems and the stringent requirement imposed by various services wishing to make use of such complex systems. In order to well maintain a large scale of WSN, such as dynamic registration of sensor devices and monitoring sensor performance, IoT device management, also known as DM authorities, should be able to provide a reliable and efficient way to remotely monitor and control sensor devices. This does provide a motivation to recent global IoT M2M related standardizations. In particular, the One M2M Global Initiative has been formed to develop one globally agreed specification for common service layer, which can be the basis of horizontal management platform. On the other hand, the IoTA project, which is a European research project addressing the reference model of IoT, is to develop IoT architectures in an interoperable manner. Device management is an integration of application, network, and also the system. In essence, it includes provisioning and management, configuration of network parameters, firmware upgrades, and also performance monitoring. As a result, a number of DM standards are emerging, such as TR069 for automatic configuration of set-top box, ISO IEC 14543 for home and building automation, and field device integration for unified management of all field devices. However, none of these standards can directly be used on IoT devices, especially on processing and battery-restricted sensor devices. Researchers started looking at open technologies to tackle device management of WSN and found the IPv6 based solution a promising one. They proposed a framework of CoAP-based device management for WSN and developed device management-oriented function, resource identities, and protocol. Specifically, they took an approach to extend the representation state transfer paradigm in which a lightweight web server can be embedded in a resource-constrained sensor devices and map device management functions into CoAP methods. A considerable research has been done on different aspects on sensor network, but the management issue for the sensor devices is not widely explored. Although there are recent works considering to introduce management into CoAP server, they are either built on management capabilities on top of CoAP or need to support multiple protocols simultaneously. This, however, brings extra overhead to the sensor devices. Researchers have tried to develop an efficient and lightweight device management solution by extending the CoAP protocol without consuming extra resources. Now let us talk about the IETF protocol stack used in resource-constrained network. Figure 1 illustrates the protocol stack ranging from physical layer up to application layer. The IEEE 802.15.4 is a radio technology standard for low power and low data rate applications with a radio coverage of only a few meters. It has typically a maximum data rate of 250 kilobytes per second and a maximum output power of 1 milliwatt. The maximum packet size is of 127 bytes. Besides, in order to achieve energy savings, a radio power management is an essential part in media access control. The radio transceivers must be managed so that it can be switched off when there is no traffic but switched on when communication is engaged. The main focus of 6LoWPAN is on protocol optimization of IPv6 over using IEEE 802.15.4. In fact, there are two reasons to apply 6LoWPAN over IEEE 802.15.4. On one hand, consider that the maximum frame size supported by IEEE 802.15.4 is only 127 bytes, and a significant header space may be taken by other layer protocols such as MAC layer header, security header, and transport layer. On the other hand, since the minimum number of maximum transmission units specified by IPv6 is 1280 bytes, which is larger than the supported size of IEEE 802.15.4, an adaptation layer right above the data link layer to segment the IPv6 packet into small pieces is required. RPL is a distance vector routing protocol in which nodes construct a destination-oriented acyclic graph, also known as DODAG, by exchanging distance vectors and route information with the controller. Through broadcasting routing constraints, the root node filters out nodes that do not meet the constraints and select the optimum path according to the metrics. CoAP is a specialized web transfer protocol for resource-constrained nodes and networks. CoAP conforms to REST style. It abstracts all objects in the networks as resources. Each resource corresponds to a unique universal resource identifier, also known as URI, from which resources can be operated stateless. CoAP introduces two-layer structure in which the message layer is used to deal with asynchronous interactions with UDP, such as conformable, non-conformable, acknowledgement, and reset messages. On the other hand, the request-response interaction layer is used to transmit resource operation requests and request-response data. In this section, we will see about the proposed framework for efficient device management solution for WSN based on IETF Open Standard CoAP. The figure shows the interaction between an IoT client and a sensor device, especially the device component interfaces to IoT client. The researchers have proposed 5 major device management functions which are applicable to WSN. These are the registration. It is the primary function to allow a sensor device to register or re-register with a remote management server, maintain and upgrade registration information. Provisioning. It is to initialize and synchronize essential information of a sensor device with a remote management server. Management services. Once the sensor devices is well connected to a remote server, a number of essential management services should take in charge to maintain IoT services such as parameter configuration, connection diagnosis, status inquiry, and remote control. Observing. It is a unique feature of CoAP to allow sensor devices to observe resources, that is, to retrieve a representation of a resource and keep this representation updated by the remote server over a period of time. And lastly, application data transfer. It includes any application data that can be collected and delivered to the IoT clients and any other application protocols above COAP. They all share common resource on one sensor device, and we abstract these resources as parameters. The interactions with IoT client can be directly triggered with these resources via get, put, post, and delete methods provided by the core, naming and addressing of resource identities. The researchers have defined a simple model in which resources are logically organized into class. A class defines a group of resources such as the hardware class contains all the resources that can be used for provisioning purpose. A resource is identified by the following path, where the class ID, resource ID, sub-resource ID are with size of 1 byte. The method ID is 4 bits, and each bit from the most significant bit represents an authorized operation in sequence of get, put, post, and delete.
Next, we see the main features of the device management protocol used. The protocol is based on co-op. It uses a modified version of co-op, which is more efficient in current use cases. Exchange of messages are done via the transfer protocol UDP. The reason for using UDP is twofold. First, since it does not need to retransmit lost packets, nor do any sort of connection setup, uh, sending data incurs less delay. Second, multicast applications are built on top of UDP since they have to do point to multi-point. Using other protocols, the CCP would be hard since now the sender would have to keep track of multiple receivers. The reliability of transmission is ensured using uh, the co-op's inbuilt confirmable and acknowledgement messages, uh, and the co-op messages are encoded in a simple binary format. The paper describes how the TM functions can be mapped to the co-op methods. For example, if you have a function such as registration, this could be accomplished using the post, delete, or the put method. You can see that these co-op methods provide a lightweight way for the management entity to access the sensor devices. The paper also describes the local hardware setup used for the prototype. There are mainly two sensors, the camera sensor and the humidity and temperature sensor. The laptop acts as a client and retrieves sensor resources via the gateway. The border router connects the laptop to the network of two sensor devices. Next, we see how the network is configured in a prototype system. The laptop is connected to the gateway through Wi-Fi. The sensor devices are connected to the gateway using the IEEE 802.15.4 standard. In this network, can be observed that the maximum hop count can only be 2. Next, we see the interaction process between the client and the server. Since the laptop communicates via Wi-Fi and the sensor devices are configured using 802.15.4 and co-op, you need a layer to convert one form of message to another. This is where the HC proxy comes in. It consists of 3 layers. First, the HTTP request from the client is converted to a co-op request by the HTTP co-op mapping layer. This is simple since the basic set of functions is the same between HTTP and co-op. Next, the co-op request is converted to a co-op message by adding a unique message ID and also headers such as confirmable, acknowledgement, etc. Finally, the lib co-op layer defines the message structure and methods which are required to implement the co-op messages based on UDP. The earlier slides we saw how the network was configured, and now we will see how the network performs in terms of latency when compared to the well-known Internet Control Message Protocol. Ping functions were used to calculate the round-trip time for both the protocols, and it was found that co-op only exceeded the ICMP by a very low margin. It shows that the latency performance of co-op is good and can replace the existing standard. The paper describes the packet length performance of the proposed method when compared to standard co-op method. Standard co-op method, the uniform resource identifier is in human readable form, thus takes up more bytes. The proposed method uses a URI of numbers to reduce the size. This leads to the proposed method using a base data and the message length reduces as a result. Evaluate the latency and packet loss performance of the proposed method compared to the standard co-op method. A test was set up where 50 independent measurements of the request response delay and the retransmission delay were noted for a GET request of the resources. Here we can see in the histogram that majority of the tests using the proposed method have a very low delay, whereas in the case of the standard method, the results are spread over exams. Proposed method also outperforms the standard method in terms of retransmission delay and the packet loss ratio. The reason for this is that the proposed method has a less data length and hence the chance of errors in the transmission are also less. Previous tests were done in a network of maximum 2 hops. The tests were also carried out in the multi-hop network, and the results show that although the packet loss rate increases as the hop count increases, loss rate of the proposed method was always lesser compared to the standard method. The tests were also done using the cloud platform to connect devices and client instead of using a board router like in the previous test. The client connects to the cloud platform using HTTP, and the cloud converts these requests to co-op messages which can be understood by the wireless sensor device. The device then transmits the request resource back to the cloud as analysis happens and the request is sent to the client. Different data sizes was sent by the sensor device to the cloud, and the average response time was noted to be only around 4.5 seconds. This shows the proposed method can work in this configuration using the cloud. To conclude, the paper describes lightweight modified co-op method that can be used for device management in networks with devices which have very low resources. The proposed method outperforms the standard co-op in terms of latency, packet loss ratio, as well as packet length, thus making it better in the current use case of a constrained network. These results show that this method could be used in future IoT applications.